In this section, we introduce one method for computing embeddings, skipgram with negative sampling, sometimes called SGNS. The skipgram algorithm is one of two algorithms in a software package called Word2Vec, and so sometimes the algorithm is loosely referred to as Word2Vec. The Word2Vec methods are fast, efficient to train, and easily available online with code and pre-trained embeddings. Word2Vec embeddings are static embeddings, meaning that the method learns one fixed embedding for each word in the vocabulary. In Chapter 11, we'll introduce methods for learning dynamic contextual embeddings, like the popular family of BERT representations, in which the vector for each word is different in different contexts. The intuition of Word2Vec is that instead of counting how often each word, W, occurs near, say, apricot, we'll instead train a classifier on a binary prediction task. Is word W likely to show up near apricot? We don't actually care about this prediction task. Instead, we'll take the learned classifier weights as the word embeddings. The revolutionary intuition here is that we can just use running text as implicitly supervised training data for such a classifier. A word C that occurs near the target word apricot acts as gold, correct answer to the question, is word C likely to show up near apricot? This method, often called self-supervision, avoids the need for any sort of hand-labeled supervision signal. This idea was first proposed in the task of neural language modeling, when Bengio et al. And Cullibert et al. Showed that a neural language model, a neural network that learned to predict the next word from prior words, could just use the next word in running text as its supervision signal, and could be used to learn an embedding representation for each word as part of doing this prediction task. We'll see how to do neural networks in the next chapter, but Word2Vec is a much simpler model than the neural network language model in two ways. First, Word2Vec simplifies the task, making it binary classification instead of word prediction. Second, Word2Vec simplifies the architecture, training a logistic regression classifier instead of a multi-layer neural network with hidden layers that demand more sophisticated training algorithms. The intuition of skipgram is 1. Treat the target word and a neighboring context word as positive examples. 2. Randomly sample other words in the lexicon to get negative samples. 3. Use logistic regression to train a classifier to distinguish those two cases. 4. Use the learned weights as the embeddings. The classifier. Let's start by thinking about the classification task, and then turn to how to train. Imagine a sentence like the following, with a target word apricot, and assume we're using a window of plus or minus 2 context words. Lemon, a tablespoon of apricot jam, a pinch. Our goal is to train a classifier such that given a tuple WC of a target word W paired with a candidate context word C, for example, apricot, jam, or perhaps apricot, aardvark, it will return the probability that C is a real context word, true for jam, false for aardvark, probability of plus given WC. The probability that word C is not a real context word for W is just 1 minus that previous equation. Probability of minus given WC equals 1 minus probability of positive or plus, probability plus given WC. How much or how does the classifier compute the probability P? The intuition of the skipgram model is to base this probability on embedding similarity. A word is likely to occur near the target if its embedding vector is similar to the target embedding. To compute similarity between these dense embeddings, we rely on the intuition that two vectors are similar if they have a high dot product. After all, cosine is just a normalized dot product. In other words, similarity WC is approximately the dot product of C and W. The dot product C dot W is not a probability, it's just a number ranging from negative infinity to infinity. Since the elements in Word2Vec embeddings can be negative, the dot product can be negative. To turn the dot product into a probability, we use the logistic or sigmoid function, sig x. We'll use the logistic or sigmoid function sigma x. The functional core of logistic regression, sigma x equals 1 over 1 plus exponent or e to the negative x. We model the probability that word C is a real context word for target word W as probability plus given WC equals sigma C dot W equals 1 over 1 plus e to the negative C dot W. The sigmoid function returns a number between 0 and 1, but to make it a probability, we'll also need the total probability of the two possible events. C is a context word and C isn't a context word to sum to 1. We thus estimate the probability that word C is not a real context word for W as P negative given WC equals 1 minus P positive given WC equals sigmoid negative C dot W equals 1 over 1 plus e to the C dot W. Equation 6.28 gives us the probability for one word, but there are many context words in the window. Skipgram makes the simplifying assumption that all context words are independent, allowing us to just multiply their probabilities. So P positive given WC1 to L equals the product from I equals 1 to L of the sigmoid function Ci dot W log P positive given WC I to 1 to L equals the sum I equals 1 to L of log sigmoid Ci dot W. In summary, Skipgram trains a probabilistic classifier that, given a test target word W and its context window L words C1 to L, assigns a probability based on how similar this context window is to the target word. The probability is based on applying the logistic sigmoid function to the dot product of the embeddings of the target word with each context word. To compute this probability, we just need embeddings for each target word and context word in the vocabulary. Figure 6.13 shows the intuition of the parameters we'll need. Skipgram actually stores two embeddings for each word, one for the word as a target and one for the word considered as context. Thus, the parameters we need to learn more are two matrices W and C, each containing an embedding for every one of the V words in the vocabulary V. So V norm words in the norm, not what is it? Every one of the it's fine. Every one of the V words in the vocabulary V. Let's now turn to learning these embeddings, which is the real goal of training this classifier in the first place. So this is the embeddings learned by the Skipgram model. The algorithm stores two embeddings for each word: the target embedding, sometimes called the input embedding, and the context embedding, sometimes called the output embedding. The parameter theta that the algorithm learns is thus a matrix of two V vectors, each of dimension D, formed by concatenating two matrices, the target embeddings W and the context plus noise embedding C. similarity between two words is approximately their dot product. And the dot product is not a probability, it's just a number ranging from negative infinity to infinity. To turn it into a probability, we use logistic or sigmoid function, the fundamental core of logistic regression. Yep. Turn into probability, use sigmoid function. We model the probability that word C is a real context word for target W as sigmoid function returns a number between 0 and 1, but to make it a probability, we'll also need the total probability of the two possible events. That's fine. Get probability for one word, but there are many context words. Most Skipgram makes a simplifying assumption that all context words are independent, allowing us to just multiply it. probability that we get a positive for a word with context 1 to L equals the product from I equals 1 to L of the sigmoid function of the context word I dot product with the target word W. And then the log probability of positive given target word W and context I to L equals the sum from I equals 1 to L of the log of sigma C I dot W. Summary, skipgram trains a probabilistic classifier given a test target word W and its context window of L words. Assigns a probability based on how similar this context window is to the target word. The probability is based on applying the logistic sigmoid function to the dot product of the embeddings of the target word with each context word. To compute this probability, we just need embeddings for each target word and context word in the vocabulary. Intuition parameters. We'll need skipgram actually stores two embeddings for each word, one for the word as a target and one for the word considered as context. Thus, the parameters we need to learn are two matrices W and C, each containing an embedding for every one of the V words in the vocabulary V. In principle, the target matrix and the context matrix could use different vocabularies, but we'll simplify by assuming one shared vocabulary V. Let's now turn to learning these embeddings, which is the real goal of training this classifier in the first place. Learning skipgram embeddings. The learning algorithm for skipgram embeddings takes as input a corpus of text and a chosen vocabulary size n. It begins by assigning a random embedding vector for each of the n vocabulary words, and then proceeds to iteratively shift the embedding of each word W to be more like the embeddings of the words that occur nearby in texts, and less like the embeddings of words that don't occur nearby. Let's start by considering a single piece of training data. Lemon, a tablespoon of apricot jam, a pinch. This example has a target word W, apricot, and 4 context words in the L equals plus or minus 2 window, resulting in 4 positive training instances on the left below. So positive examples: W, apricot, C pause, tablespoon, W, apricot of, or, negative examples: aardvark, my, where, coaxial, 7, forever, dear, if. For training a binary classifier, we also need negative examples. In fact, skipgram with negative sampling, SGNS, uses more negative examples than positive examples, with the ratio between them set by a parameter k. So for each of these WC pause training instances, we'll create k negative samples, each consisting of the target word plus a noise word, C neg. A noise word is a random word from the lexicon, constrained not to be the target word W. The right above shows the setting where k equals 2, so we'll have 2 negative examples in the negative training set for each positive example, WC pause. The noise words are chosen according to their weighted unigram frequency, P alpha W, where alpha is a weight. If we were sampling according to unweighted frequency PW, it would mean that the unigram probability, P of the, we would choose the word the as a noise word. With unigram probability P of aardvark, we would choose aardvark, and so on. But in practice, it is common to set alpha equals 0.75, i.e. use the weighting P 3/4 W P alpha of W equals the count of W alpha, or to the alpha, over the sum for W, I think that means excluding W, count, I'm not sure, W asterisk to the alpha. Setting alpha equals 0.75 gives a better performance because it gives rare noise words slightly higher probability. For rare words, P alpha W is greater than P of W. To illustrate this intuition, it might help to work out the probabilities for an example. Give me one sec. The sum of W prime of the count of W prime raised to the power of alpha. Okay. Anyway, to illustrate this intuition, it might help to work out the probabilities for an example with alpha equals 0.75 and two events. P of A equals 0.99 and P of B equals 0.01. P of A gets reduced to 0.97 and P of B gets increased to 0.03. Thus, using alpha equals 0.75 increases the probability of the rare event B from 0.01 to 0.03. Given the set of positive and negative training instances and an initial set of embeddings, the goal of the learning algorithm is to adjust those embeddings to maximize the similarity of the target word, context word pairs, WC pause drawn from the positive examples, minimize the similarity of the WC neg pairs from the negative examples. If we consider one word context pair, word context pause with its k noise word C neg 1 to C neg k, we can express these two goals as the following loss function L to be minimized, hence the minus. Here, the first term expresses that we want the classifier to assign the real context word C pause a high probability of being a neighbor, and the second term expresses that we want to assign each of the noise words C neg a high probability of being a non-neighbor, all multiplied because we assume independence. So L equals negative log of P pause given WC pause, the product from I equals 1 to K of P neg given WC neg I, and so on. Eventually, you get to the negative of the log of the sigmoid function of C pause times W, or dot W, plus the sum of I equals 1 to the K of the log sigmoid negative C neg I dot W. That is, we want to maximize the dot product of the word with the actual context words and minimize the dot products of the word with the k negative sampled non-neighbor words. We minimize this loss function using stochastic gradient descent. Fig 6.14 shows the intuition of one step of learning. To get the gradient, we need to take the derivative of equation 634 with respect to the different embeddings. It turns out the derivatives are the following. We leave the proof as an exercise at the end of the chapter. So del L with respect to C pause equals the sigmoid of C pause dot W minus 1 times W. So the derivative of the loss with respect to the positive context is the sigmoid function of the positive context dot W minus 1 times the target word. The derivative of the loss with respect to the negative context equals the sigmoid of the negative context dot the target word times the target word. And the derivative of the loss with respect to the target word equals the sigmoid of the positive context dot the target word minus 1 times the positive context plus the sum from I equals 1 to K of the sigmoid of negative context I dot target word times negative context I. The update equations going from time step t to t plus 1 in stochastic gradient descent are thus. So C positive t plus 1 or c positive to the t plus 1 equals c positive to the t minus, let me pronounce this again. Eta, okay. So c pos to the t minus 1 equals c pos to the t minus eta times the sigmoid of c pos to the t dot w to the t minus 1 times w to the t. Or no, it's not to the t, that's just the time step. Oh, I see. And then c neg at the next time step equals c neg at the current time step minus eta times the sigmoid of c neg at the current time step dot the target word at the current time step times the target word at the current time step, and then the target word at the next time step equals the target word minus eta sigmoid of the positive context dot the target word minus 1 times the positive context plus the sum I equals 1 to k of the sigmoid of the negative context I dot the target word times negative context I. Just as in logistic regression, then, the learning algorithm starts with randomly initialized W and C matrices and then walks through the training corpus using gradient descent to move W and C so as to minimize the loss in equation 6.34 by making the updates in equation 6.38 to equation 6.40. Recall that the skip-gram model learns two separate embeddings for each word I, the target embedding Wi and the context embedding Ci, stored in two matrices, the target matrix W and the context matrix C. It's common to just add them together, representing word I with the vector target word I plus context word I. Alternatively, we can throw away the C matrix and just represent each word I by the vector target word I. As with the simple count-based methods like TF-IDF, the context window size L affects the performance of skip-gram embeddings, and experiments often tune the parameter L on a dev set. Other kinds of static embeddings. There are many kinds of static embeddings. An extension of Word2Vec, fast text, addresses a problem with Word2Vec as we have presented it so far. It is no good way to deal with unknown words, words that appear in a test corpus but were unseen in the training corpus. A related problem is word sparsity, such as in languages with rich morphology, where some of the many forms for each noun and verb may only occur rarely. Fast text deals with these problems by using subword models, representing each word as itself plus a bag of constituent n-grams, with special boundary symbols, less than and greater than, added to each word. For example, with n equals 3, the word where would be represented by the sequence where plus the character n-grams WH, WHE, her, ERE, RE. Then a skipgram embedding is learned for each constituent n-gram, and the word where is represented by the sum of all of the embeddings of its constituent n-grams. Unknown words can then be presented only by the sum of the constituent n-grams. A fast text open source library, including pre-trained embeddings for 157 languages, is available there. Another very widely used static embedding model is GLOVE, short for global vectors, because the model is based on capturing global corpus statistics. GLOVE is based on ratios of probabilities from the word-word co-occurrence matrix, combining the intuitions of count-based models like PPMI, while also capturing the linear structures used by methods like Word2Vec. It turns out that dense embeddings like Word2Vec actually have an elegant mathematical relationship with sparse embeddings like PPMI, in which Word2Vec can be seen as implicitly optimizing a function of a PPMI matrix. It's pretty cool. Visualizing embeddings. I see well in many dimensions as long as the dimensions are around 2. The late economist Martin Schubik. Visualizing embeddings is an important goal in helping understand, apply, and improve these models of word meaning. But how can we visualize a, for example, 100-dimensional vector? The simplest way to visualize the meaning of a word W embedded in a space is to list the most similar words to W by sorting the vectors for all words in the vocabulary by their cosine with the vector for W. For example, the 7 closest words to frog using a particular embeddings computed with the GloVe algorithm are frogs, toad, litoria, leptodactylidae, rana, lizard, and Eleutherodactylus. Yet another visualization method is to use a clustering algorithm to show a hierarchical representation of which words are similar to others in the embedding space. The uncaptioned figure on the left uses hierarchical clustering of some embedding vectors for nouns as a visualization method. So you see wrist, ankle, shoulder, arm, leg, hand, foot, these hierarchies. Probably the most common visualization method, however, is to project the 100 dimensions of a word down into 2 dimensions. Fig 6.1 showed one such visualization, as does Fig 6.16, using a projection method called TSNE. So that's 6.1. This is 6.17. This is 6.16. Where were we at? Here. Okay. Semantic properties of embeddings. In this section, we briefly summarize some of the semantic properties of embeddings that have been studied. Different types of similarity or association. One parameter of vector semantic models that is relevant to both sparse TF-IDF vectors and dense word-to-vec vectors is the size of the context window used to collect counts. This is generally between 1 and 10 words on each side of the target word for a total context of 2 to 20 words. The choice depends on the goals of the representation. Shorter context windows tend to lead to representations that are a bit more syntactic since the information is coming from immediately nearby words. When the vectors are computed from short context windows, the most similar words to a target word W tend to be semantically similar words with the same parts of speech. When vectors are computed from long context windows, the highest cosine words to a target word W tend to be words that are topically related but not similar. For example, Levy and Goldberg showed that using skipgram with a window of plus or minus 2, the most similar words to the words Hogwarts from the Harry Potter series were names of other fictional schools, Sunnydale from Buffy the Vampire Slayer, or Evernight from a vampire series. With a window of plus or minus 5, the most similar words to Hogwarts were other words topically related to the Harry Potter series, Dumbledore, Malfoy, and Half-Blood. It's also often useful to distinguish two kinds of similarity or association between words. Here, let me just make a note of the context window thing. It's also often useful to distinguish two kinds of similarity or association between words. Two words have first order co occurrence, sometimes called syntagmatic association, if they are typically nearby each other. Thus, wrote is a first order associate of book or poem. Two words have second order co occurrence, sometimes called paradigmatic association, if they have similar neighbors. Thus, wrote is a second order associate of words like said or remarked. Syntagmatic. Is this spelled wrong? Syntagmatic. Nope, that's right. Sometimes called syntagmatic association. Word co-occurrence. Okay. Analogy, relational similarity. Another semantic property of embeddings is their ability to capture relational meanings. In an important early vector space model of cognition, Rumelhart and Abramson probably, proposed the parallelogram model for solving simple analogy problems of the form A is to B as A star is to what. In such problems, a system is given a problem like apple is to tree as grape is to what, i.e. apple, and must fill in the word vine. In the parallelogram model, illustrated in figure 615, which is right here, the vector from the word apple to the word tree equals tree vector minus apple vector is added to the vector for grape vector. The nearest word to that point is returned. In early work with sparse embedding, scholars showed that sparse vector models of meaning could solve such analogy problems. But the parallelogram method received more modern attention because of its success with word-to-vec or glove vectors. For example, the result of the expression king minus man plus woman is a vector close to queen. Similarly, Paris minus France plus Italy results in a vector that is close to Rome. The embedding model thus seems to be extracting representations of relations like male to female or capital to city of, or even comparative superlative as shown in Fig 16 or 616 from Glove. So here you see man relates to woman, similarly to how sir relates to madame, or how heir relates to heiress, or how uncle relates to aunt. This is honestly beautiful. This is just crazy to look at, right? Darker to darkest as softer to softest. Keep this zoomed in a little bit better. So for A to B as A star to B star problem, meaning the algorithm is given vectors A, B, and A star and must find B star, the parallelogram method is thus B star hat equals argmin x distance x B minus A plus A star with some distance function such as Euclidean distance. Hmm. So for a star problem, vectors, math. Parallel. So long to type out these bold-faced letters in LaTeX. I wish there was a simpler way. Maybe there is and I just don't know it. But oh well. This is gonna have to suffice for now. Math BF. Cool. Distance from x, b minus a plus a star, argument x. Cool. There are some caveats. For example, the closest value returned by the parallelogram algorithm in Word2Vec or GloVe embedding spaces is usually not in fact b star, but one of the three input words or their morphological variants, i.e. cherry is to red as potato is to x, returns potato or potatoes instead of brown. So these must be explicitly excluded. Furthermore, while embedding spaces perform well if the task involves frequent words, small distances, and certain relations, like relating countries with their capitals or verbs to nouns with their inflected forms, the parallelogram method with embeddings doesn't work as well for other relations, and indeed Peterson et al. 2020 argued that the parallelogram method is in general too simple to model the human cognitive process of forming analogies of this kind. Okay, embeddings in historical semantics. Embeddings can also be a useful tool for studying how meaning changes over time. By computing multiple embedding spaces, each from text written in a particular time period, for example, Fig 617 shows a visualization of changes in meaning in English words over the last 2 centuries, computed by building separate embedding spaces for each decade from historical corpora like Google Ngrams and the corpus of historical American English. A TSNE visualization of the semantic change of 3 words in English using Word2Vec vectors. The modern sense of each word and the gray context words are computed from the most recent modern time point embedding space. The modern sense of the word and the gray context words are computed from the most recent modern time point embedding space. Earlier points are computed from earlier historical embedding spaces. The visualizations show the changes in the word gay from meanings related to cheerful or frolicsome to referring to homosexuality, the development of the modern transmission sense of broadcast from its original sense of sowing seeds, and the pejoration of the word awful as it shifted from meaning full of awe to meaning terrible or appalling. Bias and embeddings. In addition to their ability to learn word meaning from text, embeddings, alas, also reproduce the implicit biases and stereotypes that were latent in the text. As the prior section just showed, embeddings can roughly model relational similarity. Queen, as the closest word to king, minus man plus woman, implies the analogy man is to woman as king is to queen. But these same embedding analogies also exhibit gender stereotypes. For example, Boluk Basi et al. Find that the closest occupation to computer programmer minus man plus woman in Word2Vec embeddings trained on news text is homemaker, and that the embeddings similarly suggest the analogy father is to doctor as mother is to nurse. This could result in what Crawford and Blodgett call an allocational harm, when a system allocates resources, jobs, or credit unfairly to different groups. For example, algorithms that use embeddings as part of a search for hiring potential programmers or doctors might thus incorrectly downweight documents with women's names. It turns out that embeddings don't just reflect the statistics of their input, but also amplify bias. Gendered terms become more gendered in embedding space than they were in the input text statistics, and biases are more exaggerated than in actual labor employment statistics. Embeddings also encode the implicit associations that are a property of human reasoning. The implicit association test measures people's associations between concepts, like flowers or insects, and attributes like pleasantness and unpleasantness by measuring differences in the latency with which they label words in the various categories. Using such methods, people in the United States have been shown to associate African American names with unpleasant words more than European American names, male names more with mathematics, and female names more with arts, and old people's names with unpleasant words. Caliscan replicated all these findings of implicit associations using glove vectors and cosine similarity instead of human latencies. For example, African American names like Leroy and Shaniqua had a higher glove cosine with unpleasant words, while European American names like Brad, Greg, and Courtney had a higher cosine with pleasant words. These problems with embeddings are an example of a representational harm, which is a harm caused by a system demeaning or even ignoring some social groups. Any embedding-aware algorithm that made use of word sentiment could thus exacerbate bias against African Americans. Recent research focuses on ways to try to remove these kinds of biases, for example, by developing a transformation of the embedding space that removes gender stereotypes but preserves definitional gender, or changing the training procedure. However, although these sorts of debiasing may reduce bias in embeddings, they do not eliminate it, and this remains an open problem. Historical embeddings are also being used to measure biases in the past. Garg et al. Used embeddings from historical texts to measure the association between embeddings for occupations and embeddings for names of various ethnicities or genders. For example, the relative cosine similarity of women's names versus men's to occupation words like librarian or carpenter across the 20th century. They found that the cosines correlate with the empirical historical percentages of women or ethnic groups in those occupations. Historical embeddings also replicated old surveys of ethnic stereotypes. The tendency of experimental participants in 1933 to associate adjectives like industrious or superstitious with, e.g., Chinese ethnicity, correlates with the cosine between Chinese last names and those adjectives using embeddings training on 1930s text. They also were able to document historical gender biases, such as the fact that embeddings for adjectives related to competence, smart, wise, thoughtful, resourceful, had a higher cosign with male than female words, and show that this bias has been slowly decreasing since 1960. We return in later chapters to this question about the role of bias in natural language processing. Evaluating vector models. The most important evaluation metric for vector models is extrinsic evaluation on tasks, i.e., using vectors in an NLP task and seeing whether this improves performance over some other model. Nonetheless, it is useful to have intrinsic evaluations. The most common metric is to test their performance on similarity, computing the correlation between an algorithm's word similarity scores and word similarity scores assigned by humans. WordSim 353 is a commonly used set of ratings from 0 to 10 for 353 noun pairs. For example, plain car had an average score of 5.77. Simlex 999 is a more complex dataset that quantifies similarity, cup mug, rather than relatedness, cup coffee, and includes concrete and abstract adjective, noun, and verb pairs. The TOEFL dataset is a set of 80 questions, each consisting of a target word with 4 additional word choices. The task is to choose which is the correct synonym, as in the example, levied is closest in meaning to, imposed, believed, requested, and correlated. All of these datasets present words without context. Slightly more realistic are intrinsic similarity tasks that include context. The Stanford Contextual Word Similarity, SCWS, dataset and the Word in Context, WIC, dataset offer richer evaluation scenarios. SCWS gives human judgments on 2003 pairs of words in their sentential context, while WIC gives target words in 2 sentential contexts that are either in the same or different senses. The Semantic Textual Similarity task evaluates the performance of sentence-level similarity algorithms, consisting of a set of pairs of sentences, each pair with human-labeled similarity scores. Another task used for evaluation is the analogy task, discussed on page 24, where the system has to solve problems of the form A is to B as A star is to B star, given A, B, and A star, and having to find B star. A number of sets of tuples have been created for this task, covering morphology, city is to cities as child is to children, lexicographic relations, leg is to table as spout is to teapot, and encyclopedia relations. Beijing is to China as Dublin is to Ireland, some drawing from the SemiVal 2012 Task 2 dataset of 79 different relations. All embedding algorithms suffer from inherent variability, for example, because of randomness in the initialization and the random negative sampling. Algorithms like Word2Vec may produce different results even from the same dataset, and individual documents in a collection may strongly impact the resulting embeddings. When embeddings are used to study word associations in particular corpora, therefore, it is best practice to train multiple embeddings with bootstrap sampling over documents and average the results. Summary. In vector semantics, a word is modeled as a vector, a point in high-dimensional space, also called an embedding. In this chapter, we focus on static embeddings, where each word is mapped to a fixed embedding. Vector semantic models fall into 2 classes, sparse and dense. In sparse models, each dimension corresponds to a word in the vocabulary V, and cells are functions of co-occurrence counts. The term document matrix has a row for each word term in the vocabulary and a column for each document. The word context or term matrix has a row for each target word in the vocabulary and a column for each context term in the vocabulary. 2 sparse weightings are common. The TF-IDF weighting, which weights each cell by its term frequency and inverse document frequency, and PPMI, point-wise positive mutual information, which is most common for word context matrices. Dense vector models have dimensionality 50 to 1,000. Word2Vec algorithms like skipgram are a popular way to compute dense embeddings. Skipgram trains a logistic regression classifier to compute the probability that 2 words are likely to occur nearby in text. This probability is computed from the dot product between the embeddings for the 2 words. Skipgram uses stochastic gradient descent to train the classifier by learning embeddings that have a high dot product with embeddings of words that occur nearby and a low dot product with noise words. Other important embedding algorithms include GLOVE, a method based on ratios of word co-occurrence probabilities. Whether using sparse or dense vectors, Word and document similarities are computed by some function of the dot product between vectors. The cosine of two vectors, a normalized dot product, is the most popular metric.